Continuing on with our chapter here, chapter 5, and our moles and grams. Before we continue on, any questions on any of those calculations? Molar mass, Avogadro's number, anything like that? Okay, so the next thing we're going to talk about is we're getting into calculating empirical formulas, molecular formulas. But the first thing that we also want to kind of talk about is what a lot of empirical formulas, molecular formula type problems will sort of give you in terms of information, and that is the percent composition by mass. So the percent composition by mass is basically the percentage of each element by mass that's in a particular compound. And to calculate it, you basically take the mass of that particular element in that formula, you divide it by the molar mass of the entire formula, and you times it by 100. And so, for example, here, if we look at our C2H6O and we calculate our molar mass, which I think we did on a previous problem there, is 46.07 grams per mole. And it's worked out down here on the bottom as well. If we wanted the percentage of carbon by mass in this compound, in the formula, there are 2 carbons, so we would take the mass of the 2 carbons, so 12.01 grams per mole times 2. We would divide it by the molar mass of the entire compound, and we would times it by 100%. And that would tell us, based on mass here, that carbon is roughly about 52.14% of the compound by mass. We could also do the same thing for our hydrogen here. So to figure out the percentage of hydrogen, we would take 6 times the molar mass of just the hydrogens divided by the molar mass of the entire compound. And once again, we'll times it by 100% in this case. And that would get us 6 times 1.008 divided by 46.07 times it by 100. And it's about 13, we'll call it. So 13.13% by mass hydrogen. And we could do the last part of the calculation the same way here for our oxygen. Our percentage of oxygen in this formula is there's only 1. Would give us 16 grams per mole, which is the mass of the 1 oxygen, divided by the mass of the entire compound. And once again, here we will times it by 100. And we will end up with 16 divided by 4607 times it by 100, roughly 34.73% by mass oxygen. When we're all done, obviously we have all the elements that are in this particular compound. So when we add up our percentages, they should hit about 100. They may be a little bit more, maybe a little bit less with rounding, but they should be in obviously the ballpark there of 100 in this particular case. 52.14 plus 13.13 and 34.73 hits 100 on the nose, so that's pretty good. Also, you could have, if you wanted to, right, since these are the only 3 elements in this particular compound, once you got the percentages of carbon and hydrogen, I could have subtracted it from 100, right, to get the percentage there, or take 100 minus those percentages to get the percentage of oxygen in this case. So that's an alternative way. Obviously, you could get the last one since it all has to add up to 100% in that case. This is basically by mass, mostly carbon, right? Followed by oxygen and a little bit of hydrogen there by mass as well. That is why if you think about the problem we did earlier, where we got, I think there was about 12 grams of carbon in that 26 grams of ethanol, which is this compound here. About 50% of 23 grams or 24 grams is about 12 grams, right? So that is 52% is about 12 grams. So that's why we ended up with 12 grams of carbon when we did that, because by mass, that compound contains about 52% carbon. Any questions on that there? So percent composition by mass, obviously you do need to be able to calculate the percent composition by mass. but it does show up when we calculate the empirical formula in problems, and it's given to you a lot of times in problems. So let's talk about the empirical formula and really the molecular formula. So the empirical formula is the simplest whole number ratio of what is present. While the molecular formula tells us exactly the number of atoms present for each element. So for example, if we had a molecular form of H2O2, which is hydrogen peroxide, that is 2 hydrogens for every 2 oxygens. That is the same ratio of, if you divide everybody by 2, basically 1 hydrogen for every 1 oxygen. And that would be the empirical formula in this case for it, which is HO. If we had C2H6, that is a molecular formula. If we have 2 carbons for every 6 hydrogens, we could basically reduce this down and still get whole numbers by dividing everybody by 2. That would be the same as 1 carbon for every 3 hydrogens, right? And that would give us an empirical formula of CH3 in this case. So if you actually have the molecular formula and you want the empirical formula, basically what you would do is reduce it down by a common number. The goal is it does have to be whole numbers, right? So you can't have on the subscripts, which are moles, you cannot have a decimal or anything like that. So they do have to be whole numbers when you do that. Now, if we have something like water, which is H2O, we have 2 hydrogens for every 1 oxygen. Can I reduce that down any more in this case and still get whole numbers? I cannot, right? So in the case of water, that is both the molecular formula and the empirical formula. It is the same, and that happens with a lot of things. By the way, when we put an ionic compound together, when we take something like calcium and chloride and we put it together, we do it in the simplest way to get to 0, which means that all ionic compounds are empirical formulas because you put them together in the simplest way to get to a 0 charge. So all ionic compounds are basically those empirical formulas. Any questions on that there? Now, we talked about percent composition by mass. If we were to calculate the percent composition, for example, of each of these elements here in hydrogen peroxide, that would be 2 times our 1.008 for our hydrogen, plus 2 times our 16 for our oxygen. That will give us a molar mass of this particular molecular formula of 2 times 1.008 plus 2 times 16, 3402. So the percentage of hydrogen in H2O2 is 2 times 1.008 grams per mole divided by 3402 grams per mole times 100%. And if we do that, that tells us that we have about 5.926% hydrogen. Because oxygen is the only other element there, the percentage of oxygen should be 100% minus 5.926%. So if I want to just quickly do it that way, it's about 94.07% oxygen in this case. You obviously could still do the same calculation and you'll get the same answer, obviously, but that's just, again, a quick way to get the other one. First off, any questions on those calculations? Is the percent composition by mass of my empirical formula different than my molecular formula, or should they be the same? They actually will be the same. So let's just see real quick. We got 1.008 grams per mole plus 16 grams per mole. And that will give us a molar mass for our empirical formula in this case of about 17 here and some change. We'll call it 1701. So if we did the percentage of hydrogen in our empirical formula, we'd have 1.008 grams per mole divided by 1701 grams per mole times 100%. 1.008 divided by 1701 times it by 100 gives us a percentage of 5.926% hydrogen. And obviously, again, if we subtract from 100, we will hit the same number there. For our other percentage that we had, 94.07% oxygen. So the percentage of each of these elements in both the empirical formula and molecular formula are going to be the same because frankly, they're just simple ratios of each other, right? So we end up with really the same percent composition by mass. Any questions first off on molecular formulas, empirical formulas, percent composition? All right. So now that we see how we can calculate the empirical formula from the molecular formula, in a lot of cases, you actually do have to calculate the empirical formula yourself. And there's several steps that you want to follow when you do calculate the empirical formula. And to calculate the empirical formula, there's a few steps. So let's list those here as to what we should do. So to calculate the empirical formula, if you are given the percent composition by mass, which is very common, we want to really turn those percentages into grams. And when you have a percentage, you want to turn it into sort of a usable number. You usually assume you have how much of it. Like if I got 50% on the exam, I got probably how many points out of 150, right? So we usually will assume 100 grams because that will keep the percentages the same number. You can assume as many grams as you want, but then that changes the number. So, you know, if you have 82% carbon, you got 100 grams, you have 82 grams of carbon. So it just keeps the numbers the same. Once we have all of our elements into grams, we then want to convert the grams to moles using the molar mass, obviously from the periodic table. So this is also something that people sometimes will mess up on, for example, especially when they deal with elements that are diatomic elements like O2, N2, H2. They're not by themselves in these compounds, right? When you're calculating an empirical formula. So they're just like the element by itself, one single. So when you go for the molar mass of something like hydrogen or oxygen, it is the 1.008 and the 16 grams. You don't need to do H2 because if it was H2, then what are you calculating? You don't actually know how many hydrogens you have or how many oxygens you have. So you just want to do it based on the molar mass of the element by itself. Once you have everybody converted into moles, so all the elements converted into moles, and I'm just going to do an example here. Let's just say we had A and B and we calculated 2 moles of A and we got like 4 moles of B. Once we have the moles of all the elements that are involved here, the next thing that we want to do is actually divide by the smallest number of moles. So in my example here, 2 is the smallest number of moles that we got. So we would divide both of these guys by 2 moles. And that would give us 1 for our A. And in this case, it will give us 2 for our B. Now, if we divide by the smallest number of moles and we hit whole numbers like we just did there, then congratulations, that is your empirical formula. But in this case, it would be AB2 would be your empirical formula in this particular case. Now, let's say, for example, though, that things didn't come out exactly perfect like that, which sometimes they do not. So let's just say another example. And we converted everybody to moles. Let's say we had our 2 moles of A, but in this case, we had 5 moles of B. So again, in this case, we would be dividing by 2. Which is our smallest. That gives us 1. But in this case, it gives us like 2.5 as our number that we get here, which would give us an empirical form of A, B, 2.5. And that is not a good number, right? Because it is not a whole number. So this is considered too far to round. Yeah. So when you are calculating empirical formulas in book problems, probably test problems, quiz type problems, the only place that you are okay to round is if it's like really close to the whole number. So either right before the whole number below it or a little bit above it, you can round back down. But something that typically ends in something like this, 0.5 is common. 0.33 is another sort of common ending that you get. These are too far to round. So what you have to do in this situation is figure a number that you can multiply that one by that will turn it into a whole number. So you could just do a little trial by error. If you take 2.5 times 1, you still got 2.5. Say 2.5 times 2, that looks like a 5 in that case. So that 2 is the factor by which we want to multiply this empirical formula by. And we want to make sure we multiply everybody by that 2, not just the guy that's the decimal in this case. So we would multiply this guy by that factor, and we would end up with A2B5, and that would be the proper empirical formula. So very common, you'll get these sort of endings that are really too far to round. So you got to find this sort of common number to multiply by to get it to sort of a whole number. Now, like our experiment where you physically, experimentally determine the empirical formula, a lot of times you can round in that type of thing because it's an experiment, but mainly in book type problems or test type problems, it usually needs to be really close, just below the whole number or just above the whole number to sort of round. Any questions on those steps there? Okay, then let's try one with some real numbers maybe. All right, so once you try this, determine the empirical formula of this compound that's been found to have 24.75% potassium. It's all by itself up there on top. 34.77% Mn and 51% oxygen. Let me give you some of these numbers that might be helpful. So potassium is 3910. Mn is I think it's 54, it's 94. Getting old, I can barely read that periodic table, but I think it says that, I hope. And oxygen is 16 here. Get the magnifying glass out, maybe. I don't know. I'll hold it farther. Okay, let's take a look and see. So here we are given, as we've been talking about, the percent composition by mass. You do want to, when you are given the percentages here, just quickly give it a look and make sure that they do add up to 100%. If by some chance they don't add up to 100%, then you're probably missing something and you would have some information, obviously, to probably figure it out. But in this case, if we kind of look at it, we are shooting there about 100%. So we're not missing any elements, but you do want to make sure you always kind of look at that to make sure everything sort of adds up. With that being said, we're going to turn these into grams, which is really our first step, and we're just going to assume 100 grams. So that keeps basically the percentages the same numbers as the grams. So that means I have essentially 24.75 grams of potassium. I have 34.77 grams of Mn, and I got me 40.51 grams of oxygen. Now that we have them converted into grams, the next really major conversion is to take these grams into moles. So we'll use the molar mass from the periodic table to do so. So for our potassium, that's going to be 3910 on the bottom there, so that the grams cancel. We end up with moles. For our Mn, we'll do the same type of calculation here, 5494 grams on the bottom, mole up on top. And for our oxygen would be 16 grams per mole. Again, all this comes from the periodic table, which is our molar mass of each of these. So taking 2475, dividing it by 3910, gonna get us a 0.63299 moles of potassium. 3477 divided by 5494 gets us 0.63287 moles of Mn. And lastly here, 40.51 divided by 16. Again, I'm not rounding too much here, so we don't, get a little bit of rounding error at the end or anything like that. Take it to a few extra digits, does not hurt in this case. So basically, we have our mass percent. We then convert it to moles. The next thing that we want to do is look at the moles, and we want to divide everybody by the smallest number of moles. In this particular case, it's kind of a toss-up, but it looks like the Mn just barely edges out everybody else there for the smallest. So we're essentially going to divide everybody here by the 0.63287. 0.63287 and divide by 0.63287. When we do that for potassium, it gives us a 1. When we do it for Mn, it gives us a 1. And when we do it for our last guy there, it's going to give us basically a 4. 4.0006 looks like close enough for 4. That essentially hit us all whole numbers in this case, which means that is going to be our empirical formula. So this would be KMnO4, which clearly you will tell me that is what? That is potassium permanganate. Yes, that is permanganate, one of those polyatomic ions. The quiz is only Tuesday. We've got a few days, so make sure we know those. Any questions on those steps, though? So we divide by the smallest. We did hit all whole numbers, so we're good to go. Again, you only need to multiply by a sort of multiple if you do not hit whole numbers as you divide by the smallest. Any questions on those steps there? So this is, I would say, a pretty basic, straightforward empirical formula problem. So let's talk about a little bit more complicated empirical formula problem. And that is what is referred to sometimes as combustion analysis. And sometimes a lot of times empirical formulas are found in the laboratory because you could do a very simple experiment like we did the other week, right? We basically added in the first experiment some chlorine to the silver. We added some, you didn't do oxygen, he did, what was your second one? Was it lead? No, tin. It was tin and oxygen we put together there on the second one. And by really just figuring out the masses, right, what we started with and what we ended with, and doing a sort of calculation, you could very simply calculate the empirical formula like we just did here. So combustion analysis is a method that is used to do a combustion reaction. And in a combustion reaction, a lot of times we have some type of organic compound, and usually that contains carbon, hydrogen, and sometimes oxygen as well. And we react it with some oxygen. And when it goes through a combustion reaction, typically an organic combustion will produce CO2 and water. And they will collect the CO2 and they will collect the water. And from the CO2 and the water, they're able to basically figure out how many grams of carbon there was originally, because all the carbon that ended up in the CO2 had to come from our organic compound. They're also able to, from the amount of water that they're able to kind of gather up there, figure out how many grams of hydrogen, as all the hydrogen that ended up in water had to come from our organic compound. Can I use the CO2 and the water to figure out how much oxygen was in my original compound? I cannot use really the CO2 or the water directly to figure it out, because part of the reaction is adding oxygen, right? So some of the oxygen that ends up in the CO2 and the water came from the O2 and not the organic guy that had the oxygen. But what we do know at this point is usually you will know the grams of the organic compound you started with, which contains basically carbon, hydrogen, and oxygen. So you can figure out the grams of carbon and subtract it, and you can also subtract the grams of hydrogen from that, and that will then tell you the grams of oxygen that was in your original compound. Conservation of mass, right? So whatever elements we started with, we should end with. So that is the idea behind this principle. Any questions on that? At this point, it will then become a regular empirical formula. Once you got the grams of everybody, you will convert them to moles. You'll then divide by the smallest moles. And then you could get to your empirical formula. So the difference with this type of problem, this combustion analysis type problem, is there's just a little bit of prep work there before you can actually get to the part that's the empirical formula calculation. First off, any questions on that there? So let's take a look at one together and we'll work through it here together. So we're going to take some ethanol and we're going to take about 11.5 grams of it. And this is sort of the setup of it. You have some oxygen being funneled in. You heat up this ethanol in the sample. The water and the CO2 will go through, and they have some, obviously, some absorbers, so basically to catch each of the water and the CO2. And we'll have some unused oxygen that will come out the back end. So they're able to collect basically 22 grams of CO2 in this experiment and also collect 13.5 grams of H2O. So we're going to use each of those values to figure out the grams of carbon and the grams of hydrogen. And this is going to come back to what we were talking about at the beginning of the day today. We're not interested in CO2, all of it. We're just interested in the carbon part. So we're going to use the formula like we did earlier today, that kind of 1 mole to 1 mole relationship to figure out how much carbon there was. So let's start with that. We're going to use the CO2 to figure out how many grams of carbon there was. So starting with 22 grams of CO2, if I take my CO2 formula, I know that 1 mole of CO2 will give me how many moles of carbon? 1 mole of carbon in this case, again, just from the formula. Just like we did earlier today, we can't really use that relationship until we convert our CO2 into moles. So we will need the molar mass to do that. So there's 12.01 grams of carbon plus 2 times 16 grams of oxygen. Going to give us a 44.01 grams per mole as the molar mass of CO2. We're going to use that as a conversion factor to go from grams of CO2 to moles. So 44.01 grams per mole of CO2. At this point, if I stop, the grams of CO2 will cancel and I will be left with moles of CO2. And this is the part where we're now going to transition from moles of CO2 to just carbon, which is essentially what we're interested in. So we're going to use that relationship from the formula here. That 1 mole of the CO2 will give us basically 1 mole of just carbon. So we'll do that. 1 mole of CO2 will get us 1 mole of carbon. And I'll grab me an answer here, and I'll tell you why I did it later on, but I'm going to grab an answer right here. That's going to give me 0.49989 moles of carbon. I do want to eventually figure out how many grams of carbon that is. So now I'm going to use the molar mass of carbon at this point, which again is 12.01 from the periodic table, to convert my moles of carbon into grams. And that will get me 6.0036 grams of carbon. So essentially, from that 22 grams of CO2 that they collected, about 6 grams of it, that carbon, came from our original compound, our original 11.5 gram compound of ethanol. which is this guy here, which obviously contains carbon, hydrogen, and oxygen, right? Any questions on that calculation so far? We're going to do the exact same type of calculation here for the water, except that the water, again, is going to be the source of hydrogen that was there originally. So we're going to do it for hydrogen. So we're going to look at the water here to figure out the grams of hydrogen there was. So obviously we could use the formula for water here to get our relationship. So 1 mole of water will give me, in this case though, 2 moles of hydrogen, right? So we will have 2 moles of hydrogen. And just like with the CO2, we do need the molar mass to convert our water into moles, so we could use that relationship. So there are 2 times 1.008 grams per mole plus 16 grams per mole. Gives us a molar mass per water of 18.02 grams per mole. So starting with our water, they collected 13.5 grams of water. We're going to convert it into moles using the molar mass of water here. That will cancel out the grams. And now we could use our relationship from the formula to go from water to just hydrogen in this case. And that is 1 mole of water gives us 2 moles of hydrogen in this case. The moles of water will cancel. I am again going to get a number here, 13.5 times 2 divided by 18.02. Going to give us 1.49834 moles of hydrogen. Once again, here we do want the grams of hydrogen, so we're going to use the molar mass of hydrogen here, which is our 1.008. And we're going to put that up on top, so we end up with grams. So we'll take that number and multiply it by 1.008. Going to give us a 1.5103 grams of hydrogen. So out of that 13.5 grams of water they collected, 1.51 grams was basically hydrogen that originated from our ethanol that we sent through this combustion reaction. Just like originally we had 6 grams of carbon that came out of that original ethanol. Any questions on that so far? The missing element here is that oxygen, which we cannot get directly from either the CO2 or the water because we're adding oxygen. But what we do know is our original sample had a mass of 11.5 grams, and that contained carbon, hydrogen, and oxygen. So if I subtract the grams of carbon that we calculated, and if I subtract the grams of hydrogen that we calculated, that will get rid of that and that. That will leave me how many grams of oxygen there are. And that's 11.5 minus 6.0036 minus 1.5103. It's going to give me roughly 3.9861 grams of oxygen in this case. We quickly just add up our grams of each of the elements. We got about 6 grams, about 1.5, and about 4. That's roughly 11 grams or so, right? Which is what our original sample mass was. Any questions on any of that calculation there? All right. Now that I have the grams of each of the elements in ethanol, I can now start actually the empirical formula part of the calculation. That means I need to take the grams to moles. And this is why I originally got a number here, because I don't need to go back and do it because I have the number of moles of carbon already. And I have the number of moles of hydrogen already. So really all I have to do is convert my oxygen into moles here. So we'll do that by dividing by 16 grams per mole for oxygen. And that will give me, sometimes it's good to think about what you have to do at the end of the calculation, so you're not going to go back and recalculate certain things. 0.24913 moles of oxygen. And now I have my moles of oxygen in this case, right? Any questions on that there? All right, so now that I have all the moles, I'm going to flip the page here and recopy them over. So I got here 0.49989 moles of carbon. We had 1.49834 moles of hydrogen. And we calculated that we had 0.24913 moles of oxygen. Now that we have it in moles, we next want to divide by the smallest. So in this case, it looks like it is the oxygen that is the smallest number of moles. So we're going to divide everybody by the moles of oxygen, as it is the smallest number of moles. And let's see what we get here. We obviously get a 1 there. We take our 1.49 and divide it by 0.24913. We get roughly a 6. And if we take our 0.49989, and again, if you look at your calculator, you get something like 6.01. That is close enough to round, obviously, to 6 in that case. Divided by 0.24913 gets us 2.006, which obviously is a 2. We did get whole numbers in this case, which means our empirical formula for ethanol is C2H6O in this case. Yeah. Any questions on those steps? So a combustion analysis is a very common procedure where they do a combustion reaction, collect that water, collect the CO2. That allows you to figure out how many grams of carbon was there originally, how many grams of hydrogen was there originally, and adding those together and subtracting from the mass of your original sample will give you the grams of oxygen. Once you do those calculations, then it rolls into just a basic sort of empirical formula. So a little bit more prep work up front in these type of calculations involving combustion analysis. Any questions on that there? All right, so that would I say would be a little bit more involved empirical formula type problem, but definitely doable. Right. So let's talk about then how we calculate. In case you missed it, we'll put it up here one more time. Pretty red. There we go. They got the same thing. That's good. They did. Let's talk about how we calculate the molecular formula. So to calculate the molecular formula, you really need 3 things. You need the empirical formula. So either the empirical formula would be given to you, or you need to go through the process we just did in those couple of examples and calculate the empirical formula. Once you have the empirical formula, you also need the molar mass of the empirical formula. And lastly, you need the molar mass or the approximate molar mass of the actual compound that you're trying to figure out the molecular formula for. The good news is this guy right here is usually given to you. So usually somewhere in the problem, they'll say, hey, this thing has a molar mass of like approximately 95 grams per mole. They may also give you even a range of molar mass, like it ranges from somewhere between 90 and 100 in terms of its molar mass. Now, if they do give you a range of molar mass, you could actually choose anywhere in that range and it will pretty much come out the same. You could either choose the low end of the range, you could choose the high end of the range. Most people will probably shoot for something in the middle of the range. Yeah, so kind of use that for the calculation, but you could use the high, the low, or the middle, or anywhere in between when you do that. So what do you do with those 2 numbers? Basically, you take the approximate molar mass of the compound, which is given to you. You divide it by the empirical formula's molar mass, and it will give you a number. And that number is the number that you multiply the empirical formula by to get the molecular formula. So for example, let's say we had our empirical formula of our AB2. And let's just say that we did our calculation here and we ended up with a 4. Our molecular formula in this case would be A4B8. Yeah. So we would take this 4 and multiply it, both things by it, to get our molecular formula, which would be this guy in this case. Yeah. I will say that probably the only place where it's okay when you're doing these type of calculations to sort of round a little bit more freely than you would with the empirical formula is when you do this division here. So when you do this division, it may not always be a nice pretty whole number, and it's probably okay to round that one because the molecular formula should be a larger number than the empirical formula, and they're related by whole numbers, right? So they're whole number multiples of each other. So you can pretty much round. So for example, if you did this and you got like a 6.1, you could probably call it 6. You got like a 4.3, you could probably call it 4. You don't really want to do that when you're doing the empirical formula calculation, but here when you're trying to figure out that multiple to multiply it by, because it should be a whole number. And because a lot of times what you're given in these problems is not the for sure molar mass, but it's like the approximate or experimentally found, there's a little bit of error in there. So it's okay to round a little bit more freely when you do this calculation as to opposed to when you do the empirical formulas calculation. Any questions on that there? Okay. So go get after it here. Calculate the molecular formula here of this compound that is made up of 6.44 grams of boron and 1.803 grams of hydrogen. So boron, that looks like a 1081, I hope. So boron is 1081, and our hydrogen is 1.008. So you want the molecular formula here, which means you need empirical formula. Empirical formula is molar mass, and the approximate molar mass of the compound, which can be found usually in the problem. So see what you come up with here. Okay, let's take a look and see how you're doing. So in this case, we're looking for the molecular formula, and there's 3 things that we need. We need the empirical formula, which we are not given in this case. So we do have to go through our process to calculate the empirical formula. Once we do that, we will get the second thing that we really need, which is the molar mass of the empirical formula. So we kind of have to do those things together. The last thing that we need is the molar mass of the compound, which is actually given to us here. So approximately it is about 30 grams. So we're really just going to start out here with an empirical formula calculation. So it's already in grams, by the way, so don't ungram them. Yeah, so they're already in grams. Don't try to figure out percentages because you don't need to do that. So we already have our 6.444 grams of boron. We have our 1.803 grams of hydrogen. So once they're in grams, we want to convert them to moles. So we'll use the molar mass from the periodic table to do that. So for our boron, 1081, I think I wrote there, 1081 grams per mole. For our hydrogen, it would be 1.008 grams per mole. That's going to give us our moles of boron to be 6.444 divided by 1081, 0.59611 moles of boron. For our hydrogen, 1.803 divided by 1.008, going to get us 1.7887 moles of hydrogen. Any questions so far? So our next step in calculating the empirical formula is to divide by the smallest. So in this case, it looks like boron is the smallest. So we're going to divide everybody by the moles of boron. And that's going to give us a 1 there, bless you. And that's going to give us a 3, it looks like here. Once again, here we hit whole numbers. So that means that's going to be our empirical formula of BH3. It's our empirical formula. Any questions up to that point? So we now have our empirical formula. We have the molar mass of the compound. So the last missing piece that we need is the molar mass of the empirical formula. which obviously we can now calculate since we have it. And the molar mass of this guy would be 1081 for our boron, plus 3 times our hydrogens here. And that will give us an approximate, our molar mass for our empirical formula of, we'll call it 1383 grams per mole. So now we have the molar mass of our empirical formula. The last thing we're going to do is take the molar mass that was given to us in the problem, the approximate molar mass. We're going to divide it by the molar mass of the empirical formula. And we're not going to times it by 100, just going to divide them. And 30 divided by 1383. And here we get 2.169. So again, as I mentioned, in this case, because it's definitely an approximate sort of molar mass, it is okay to round it basically here to 2 in this case. And that would get us a empirical formula B2H6. So really, this one should be a whole number sort of ratio of the empirical formula, but because that molar mass is approximate, not maybe exact, and like I said, you could even get a range of it's somewhere in this range. You can do a little bit more rounding than normal. Any questions on that? This obviously would be our molecular formula here. Questions? Yeah.
They did the wrong.
Yeah.
You end up with
I would say, yeah, if you screwed up the experiment, that's probably a good chance that you won't get a correct empirical. Well, obviously, if you were to do it to figure out something for like what is the empirical formula, you would obviously do it more than once, probably, right? You would do multiple trials and stuff like that. So hopefully you wouldn't screw it up. Hopefully it wouldn't be as precise and screw it up every single time the same way. But ideally, that's why we in experiments, right? We do multiple trials to see if we get the same results, right? Or if it's consistently the same, right? And that's that precision and sort of we're looking at. If you do this experiment like, 100 times, 20 times, whatever it is, and you get the same number every time, there's probably a fairly good chance that that is the right number, right? If you do it like 20 times and you get like 15 different answers, there's a good chance that probably you're screwing up somewhere along the way. And you know that probably the numbers you're getting, maybe one of them might be right, but you're not really sure which one it is. So that's again why in experiments, obviously we do multiple trials to know, okay, we keep still hitting this number. So, and we're doing everything hopefully correctly, that's probably the correct number. Yeah. Other questions? All right, so let's take a look at one more here to finish it up, I think. Phosphorus oxide contains 43.64% phosphorus, 36% oxygen. It was experimentally found to have a molar mass of 283.89. What is the empirical and molecular formula here? So phosphorus is 3097, I believe. And oxygen is 16. All right, give it a go. See what you come up with there. Here we're looking for both the empirical formula and the molecular formula. So obviously we do need the empirical formula to get to the molecular formula. We also have the other piece of information that we need for the molecular formula, which is the apparent molar mass or the molar mass of the compounds, 283.89 grams. So really here, we're going to start with just the empirical formula part of the calculation. We're given the percentages of each of these elements. Quickly looking at it, we got like 56 and 44. So that's around 100%. So we're not missing any elements or anything like that. We can again assume that we have 100 grams, which will basically again turn those into the same number. So 4364 grams of phosphorus and a little 5636 action there of oxygen. Now that we have them in grams, we're going to convert them into moles using the molar mass of each of these elements from the periodic table. And that's going to be a 3097 and For our oxygen, 16 grams per mole. That's going to give us for the phosphorus here 4364 divided by 3097. We'll call it 1.4091 moles of phosphorus. For our oxygen, 5636 divided by 16 on our route here to our empirical formula, 225 moles of oxygen. We're going to divide by the smallest number of moles, which in this case looks like it is the phosphorus. So we'll divide everybody by the moles of the phosphorus. Again, we always divide by the smallest number of moles here. That's going to give us a 1 for the phosphorus. And in the case of the oxygen, not going to give us a 1. Going to give us basically a 2.5. So at this point, our empirical formula is PO 2.5. Can we leave it like that? We cannot. It does need to be a whole number here. So we kind of did this one earlier. Obviously, we took 2.5 times 1. We got 2.5. Well, 2.5 times 2 gets us 5. So that is going to be the factor that we want to multiply this empirical formula by. We're going to multiply this guy basically by 2. And that will give us P2O5 as our empirical formula. Any questions up to there? Yeah. Now that we have the empirical formula, we do need the molar mass of the empirical formula so that we can get to our molecular formula. So this is going to be 2 times the mass of phosphorus, 3097, plus 5 times the mass of oxygen. And that's going to give us 2 times 3097. That's not going to work. 2 times 3097. Plus 5 times 16 looks like 141.94, 141.9 grams per mole. So we're going to take the molar mass that they gave us, that is for the compound. We're going to basically divide it by the molar mass here of our empirical formula. And in this case here, if you punch it in right, would probably help as well. Let's try that there, 141.9. Looks like a 2 in this case. So that 2, once again, is what we're going to multiply the empirical formula by. And that would give us P4O10 in this case as our molecular formula. Sometimes and rarely these days, but years ago in books, sometimes people will write the molecular formula like this and put the little 2 on the bottom. I'm personally not a fan of it. I'd rather just multiply it out and get the formula like that. But you might sometimes occasionally still see people write it like that. But I think you should probably multiply it out so that you do get the molecular formula. Any questions on that particular one? All right, so before we finish here, I do want to do this one and show you this problem. One other way that you could do this problem, that if you would like to do it the other way, you could do it. So let me just show you sort of an alternative way that you could have solved this problem and end up probably with the same answer. And then we'll talk about everything else and wrap it up here. All right, so the alternative approach, and I'll just leave our final answers here on the right, and I'll do it over here on the left. Our alternative approach in this case is we actually do have the percentages given to us of each of these elements, and we do know the actual molar mass of the molecular formula, right, or the compound itself. So we could actually start with getting the molecular formula first and then working to the empirical formula, which is sort of another approach that you could actually do on that. And that's because when we add up these percentages, they do add up to 100. So that means out of that 283, 43% of it or so is phosphorus grams, and 56% of it is oxygen grams. So if I take the phosphorus and turn my percentage into a decimal, 0.4364, which is taking the 43.64% and dividing by 100, basically, and I times it by the molar mass, which is 283.89 grams, that would tell me that I have 4364 times 283.89 grams, around 123 I will call it 890 grams of phosphorus. I could do the exact same thing here for my oxygen, convert that into a decimal, 0.5636 times the molar mass of the molecular formula or the actual compound. And that will tell me in terms of grams of oxygen in this case, out of that 283.89, I got about 160 grams of oxygen. Any questions on that so far? Now that I have the grams, I can actually use the molar mass of each of those elements to get the moles. So we'll take the 123.890 grams of phosphorus. We'll divide it by the molar mass there of phosphorus, which is 30.97 grams per mole. So we'll take 123.89 divided by 30.97. That's going to hit me 4 moles of phosphorus. I could also do the same thing here, 160 grams of oxygen divided by the molar mass of oxygen. And we take 160 divided by 16 gets us a 10 moles of oxygen. That is my molecular formula right there. And now that I have my molecular formula, all I have to do is, that is a 4 phosphorus to 10 oxygen ratio, which means I could divide everybody by 2 and still have whole numbers. Gives me 2 phosphorus for every 5 oxygens. And now I have my empirical formula. So if you do have the percentages given to you and the molar mass of the compound, you could actually start by getting the molecular formula and then simply reduce it down to the simplest whole numbers, and you'll have your empirical formulas. Or you could do it the other way, whichever way you like. They both come out the same. Now, obviously, you could not do that on some of the previous problems because we didn't have the percentages right, and maybe we don't have the actual molar mass of the compound itself. But in this case, you could go that way if you prefer. Options, good, yes, I suppose. Any questions on how to calculate molecular formulas, empirical formulas, percent compositions? Everybody? I divide by 2 because this is the molecular formula, and the empirical formula is the simplest whole number ratio that's present. So basically, in the molecular formula, there's 4 phosphorus for every 10 oxygens. So the only way that we could reduce it down and still get whole numbers is divided by 2. If we divide by any other number, we won't get whole numbers. And the empirical formula always has to be the whole number ratio of what's the molecular formula. Other questions?